Alright, holy hell, hopefully this is just 1 or 2 minutes, and then we have an hour and a half. But this was the take-home point from column buckling. We were reading a textbook, and you know what I mean, we're just trying to wing it, we're trying to do the best we can, but you get into some subjects where you're just like, I don't see it. And so here's was the full recap. Let's see if we can do it in 2 minutes. Now, this is a column, and it's going to be pivoted at B, and we're going to put this hella stiff spring. If you just imagine this is just a hella stiff spring, I can't even move it, you know what I mean? Think about that. And then we're just going to apply a load. It could be just a little bag of rice, you know what I mean? That's what we do. And this experiment you can totally do for yourself. And then so this spring, because it's a rotational spring, is going to be like, hey, if an angle develops, then we get some sort of resistance in the spring that's going to be trying to unspring itself. And in a rotational direction, that's going to be a moment, you know what I mean? Because forces are causing the spring to fold into this V shape, and the spring is going to undo that. And then so hell yeah. And then the first one that I didn't get during the video, well, let's look at what the spring constant is. So right here it says the moment is equal to the spring constant times the angle. So if I just have this system no force, and I'm pulling out like a bow onto this, you know, corner B, and let's say B is in, like this is a roller track. So, you know, if I do put an outward force at B, this roller track's going to catch up there. It's not just going to pull off the wall. When I do pull this heavy stiff spring back, it's going to cause an angle to form, and that's where I was just like, I don't even know where the hell they're getting the 2B from. But this is, the original position was straight, and when we pull this angle, the actual angle is this. So if we look at this triangle, it's 180 degrees, if you can even consider this a triangle. And then when we pull this triangle, we do get two angles to form, theta and theta. And if this triangle is supposed to add up to 180, we have this angle right here is now 180 minus 2 theta. It used to be 180, so that's a pretty cool way to look at that. And then so therefore the moment generated in the spring, you know, even back to this equation, is just going to be the spring stiffness times the angle. And we're going to say it's 2 theta in that regard. And that's going to be the moment generated. Hell yeah. So that's but there's 2 take-home points. That was the first one. So we're doing just an equilibrium equation right here where we're just going to take one bar and we're going to say that the load down and the load up is, and then these loads are asymmetric, or, you know, we have a distance between them. This angle is real small, and this hypotenuse is L divided by 2. So this distance, you know, this is a couple, this P up, the line of action, P down, and it's going to cause a tendency to rotate this thing. So that's the load that we're applying, the small bag of rice or something. And that distance right here is going to be this hypotenuse times the sine of this angle. The angle is real small, so the sine component just goes away if it's in radians. And we have this distance right here. And now we have the moment at point B generated by this, you know, this couple. And if we take the moments at point B, it's just this load P times the distance. So we have P, L divided by 2, theta. Instead of sine theta, it's just P times this hypotenuse, sine theta, but it's just hypotenuse theta. So it's P, L divided by 2, theta. That's going to be the moment. If we use right-hand rule, this is what's going to cause this to collapse. And if we stick our thumb into the page, it's going to be a negative moment. Now, this spring is going to cause a positive moment. And a big faux pas in this, because I'm just learning this, and I related this spring to be like friction of a car. Like if you put a force down, it would just stick. And no, that's not the case. This spring is so stiff, and this BR, this beta R, is the spring constant, and that is a huge number. And so if I take this huge number times this angle, theta, then that is going to be the restoring moment. You know what I mean? So, and where this problem gets its juice is like, sure, if I put a load P down on this, and it already is starting to bend, it's going to bend like hardly anything. And then in that case, it is like, the friction thing I was talking about, that if I, you know what I mean, this, well, no, that's not the case either. Well, no, let's see. Yeah, that could be the case, where if you apply a load down, your angle is only going to match that load. You know what I mean? And so if this thing is in a position of equilibrium, and I think that has to be the case, even though they don't specify that. What they specify is that this thing is wants to be perfectly rigid, and if we do have a small load, oh, that is funny. No, so I'm getting this wrong like all the time. So this would be a fascinating one to actually set up. So let's go to the equation of equilibrium, because they're going to say that moment B, that restoring moment, which is this, it's 2 times the coefficient of rotational stiffness times the angle. So it's very similar to a spring force is equal to a spring constant times the change in length. And so, yeah, okay, yeah, no, but there is 2 parts to this. So you have the restoring force right here. So we're going to set up the experiment, but for this proof, we're just assuming the column that we made in the building is going to be totally vertical. We're going to apply a load. We're not going to expect any bowing. But then what we're going to do is physically move point B to like a really wide angle out here. And what we're going to find is this spring stiffness is so stiff that it actually takes tons of juice to and I don't forget the terminology, but just to dislocate this point, and then you let go, it is going to return to its totally vertical position. That is the general gist, because they're going to say this restoring moment is always larger than the moment causing it to buckle. And if you start, they're going to say start the process right here. And what you're going to notice is if we start the process right here, this load P goes through C and A, and there is no tendency. Like it can just do this all day. But it only is in the situation where you actually take point B and physically move it, which, an earthquake could do, or, any sort of external force could do. And then you're going to see what happens. And if this spring is hella stiff, that point goes right back. And let's go to the equation, because I wish they did this equation, had another step where you had 2B, 2 times this spring stiffness. I'm just going to say this is the spring stiffness, even though it's beta R. 2 times the spring stiffness times theta minus the load times the length, half the length, times theta. So I wish they foiled this in and had another line. Because what we're going to see is that, so that's the equation for equilibrium. If those two are equal, then we have equilibrium. Oh, hell. Yeah, this is going to be a long addendum anyway, because I'm still trying to figure it out. Every time I just kind of like, I get it, and then I kind of run into a hiccup. Because this experiment is starting from a total verticalness. So think about that. So we have a total vertical setup. We have a load P. I'm just going to say this one is real small. So the length is what it is, but this value right here is tiny, tiny, because we just didn't apply a lot of load. This is a really big number. Cool. So then when we take a really big number times the angle, and that's where we run the experiment. Then we actually take that point B, dislocate it a little bit, we generate a little bit of angle, and what we're going to see is a huge number times this small angle, and then this value right here. Let's forget the negative sign yet, because we're just looking at equilibrium. This value right here, which is real small, times that small angle, is real small. So the moment that's trying to drive the buckling is just potatoes, and this is huge. given that we moved or laterally displaced the lateral displacement of point B. So that's how this experiment is run, and I wish they just explained it so much better in this text. This is one of, like, I think the worst. I'm just going to say it. This one was difficult from just a textbook perspective to be like, what are you talking about? But hell yeah, you physically laterally displace point B, and this is always bigger. And I was just like, well, isn't there some place where it'll actually reach equilibrium? Yeah, at 0. Because this restoring moment is always, no matter what this angle is, as we move B laterally, this spring is hella stiff, returning it to its vertical, and until it gets to be vertical, then we reach equilibrium again. And so the general gist of the the hour and a half is, talking about how this is your equilibrium. I put a load that's very small, and then I try to displace point B out here. The spring is so stiff it brings it back. So it wasn't even how I thought, where, like, you know what I mean? If you had a small load, you could bring this point B out, and then it would just chill out in this position. And that's where I think this picture got me totally messed up. But now we know, you know what I mean? Like, this would be a really cool experiment to do with some sticks, some bearings, and just some small weight, and then a heavy spring. So you could be like, okay, I'm pushing down on this, and it just goes pop right back into vertical. But there's going to be a point where that's kind of interesting too, because once this load is so big, then when we displace this just a little bit, we cause a driving moment. And why, if we just displace it a little bit, does it fail? Well, we have to go back to look at this equation, how they're both a function of theta. So that's why I wish there was another line in here that says 2 times this spring constant theta minus PL divided by 2 times theta. I mean, even though you can just FOIL it through yourself. But like I said, we said this was a big number because we used a stiff spring. But then over here, the length divided by 2 don't change. But we can increase the P. We can increase the P. So this parameter right here exceeds this parameter. And then what's going to happen, this is the one that's going to cause the rotation to buckle. So then when we displace point B just a little bit, this thing is taken over, and that column is coming down. So hell yeah, I think that was under 10 minutes. But that was the whole take home. And it was just, this was a testament to be like, hey, I was doom scrolling, and I was like, nah, let's read some text. And I think it's one of the cooler things I do on this channel, like reading textbooks. I think it's you could be washing dishes for an hour and a half, and just, that'd be a long time. But anyway, you could and just watch me struggle through this. And I think it's good teaching style, because you're just like, haha, I wouldn't have struggled through that. Cool. If you wouldn't have struggled through it on this material, pat yourself on the back. But then there's going to be material that you're just like, I have no idea what the hell's going on. And so this one was like, I knew I didn't know what was going on. And I mentioned that I read through this before, but tonight was the first time I was just like, oh, thank God I get this. So now when I roll this through my head, I'm just like, okay, I get the equations. I even get what the setup they're talking about. They're always starting from the vertical. They're physically displacing that midpoint. And yeah, if you think of that spring as just hella stiff, and their picture doesn't do justice, and this one throws you off. It looks like this is an equilibrium position. This is only an equilibrium position if this says P critical, and that's where they're missing some labels. They should really say P critical up here, and then even do like a dotted dash line of this thing being in a couple different locations. But I do like this textbook. I don't know. It's just the one that I graduated with. So obviously we just said this was hell. But booyah. Alright, so now for the rest of the video, thanks for joining me. Booyah. Alright, hell yeah. So I'm doom scrolling, and so why not read some textbooks? This is Mechanics of Materials. This is James M. Gear. And we're going to be talking about column buckling. And the reason is because I fully can't wrap my mind around it from a fundamental perspective that I would like. Sometimes I like to take these physics concepts and just kind of make my own fundamentals. So I don't know if we're going to read the chapter overview, because it's usually an overview of the whole chapter, and I just get sucked into a black hole of starting to explain things. So hell yeah. So we're just going to try to read through this, might as well. You know what I mean? I can read, and then you don't have to. So the load-carrying structures may fail in a variety of ways. So cool. Columns can fail in a variety of ways. Mainly, if this force gets applied, you know what I mean? Maybe there's no bending, and it's going to fail just like a piece of, like a stud in a stud wall. You know, it's just going to shear at a 45 or whatever. Cool. And then it's depending on the type of the structure, the condition of the support, the kinds of loads, and the materials used. For instance, an axle in a vehicle may fracture suddenly from repeated cycles of loading, or a beam may deflect excessively so that the structure is unable to perform its intended functions. These kind of failures are prevented by designing structures so that the maximum stresses, that's the whole general gist of material mechanics. We have made a property called stress, which is identifying a force and seeing how much area that force acts on the structure. And it's force per area, but you could almost think of it force per volume. And I like to go one step forward and just be like, hey, this structure is made out of atoms, and there's a number of them. You know what I mean? So it's almost like force per atoms, and those atoms, those molecular bonds are holding strength. All right, hell yeah. But you have this stress, force over area. Cool. And then you have maximum values for material. So for steel, you're given like 50,000 psi, don't exceed that. And we can get an idea, it's like, hell yeah, I can squeeze a piece of steel and understand that I'm applying that pressure to it. Cool, and so those are going to be our maximum values. Now, if we're leveraging something like bowing it, you know what I mean, by taking this and it's getting bowed, well, some sort of leverage is happening. And in this case, you know, bending causes no stress in the middle, but then we get a tensioning, a lengthening on this side, and then a crunching on the other side. And so those values might be positive and then negative. And with steel, the negative value and the positive value still can't be like, you know what I mean, it's about the same in compression and tension. All right, let's move on. So anyway, yeah, you have a value for those maximum stresses. And then maximum displacements. But what we see repeatedly throughout material mechanics is one means the other. So if I hand you a length of steel, I could be like, hey, don't stretch this more than 2 millimeters. You know what I mean? Or I could say, hey, don't stretch this past, you know, this PSI. And both mean the same thing. And it's a linear relationship, which kind of probably is kind of like difficult to understand, because I don't, like, yeah, I think even very simple linear equations, you're just like, oh, one thing equals the other thing with a proportional constant. That's all it is like stress is in different units of changing length, you know what I mean? And stress is force per area. The changing length is the change in length per the entire length. So it's a percent change in length. And both those quantities are going to be the same regardless of the shape of that you make. But it's if I hand you some steel, it's going to have that property. You know, the percent change in length compared to the length that you're actually using. The force per area, you know what I mean, that you're actually using. Double the area, cool, you can double the force. Double the length, you can double the amount you can stretch it. You know what I mean? Maybe you don't want it to be able to be that stretchy, so you might want to shorten things up maybe. All right, hell yeah. And then so those are our limits. And I'm just glad that's a 5-minute introduction to material mechanics. But I don't understand why teachers just don't stress that. You know, take 5 minutes of the day is just like, hey, where are we? You know what I mean? These are our basics of material mechanics, and we're just adding to it. Cool. And then we have like numbers that are tolerable, like maybe a factor of safety. All right, moving on. And so we have strength. Strength is going to be that force per unit area. Stiffness, I guess, is like, hey, if it's stiff, it didn't move. The displacements were small, so you can have a measure of those. So if we do get an equation, things that make the displacement smaller are going to be the stiffness-related properties, You know what I mean? Hell yeah, we can maybe figure that out. Because stiffness is kind of, just looking at what properties, might cause things to displace. What causes the stiffness. Cool. All right, and so these are important factors in design, and as discussed throughout the preceding chapters. Yeah, and even this, I'm getting messed up because this is still just an introduction. So let's continue on. Another type of failing is buckling. So finally, that's what we're getting into, which is the subject matter of this chapter. We will consider specifically the buckling of columns, which are long and slender. So when I put a force on a long, slender column, I don't expect it to behave axially. Ideally, yeah, you can put almost unlimited amount of force on columns, or, not unlimited, but if you have whatever area, it can take so much pressure, and then so you have a green light. If this is a short column, you can just put a ton. But if it starts to do this, it's very little. Bending is just, like 1/10 of the loads, 1/100th of the loads in bending that you could actually put in just axial compression. So keep that in mind. Hell yeah. And so long, slender structural members loaded axially in compression will probably buckle. If a compression member is relatively slender, it may deflect laterally and fail by bending. And I think for this chapter, just assume things are always moving laterally. Just assume the worst. It's just like, can this thing move laterally? And then what we're going to see is like, hell yeah, we got 2 pins here. And it just seems like if you put a downward deflection, what other choice is this thing going to have? Sure, the molecules can be stacked. But it seems like you would want to just assume that if I'm putting a downward force, like this is happening, the worst case scenario. Now, things aren't just going to be pinned on both ends, maybe. They're rigidly straight, where we're going to get into some things where it's going to have like a straight, and then it's going to bow out and then come back. And so obviously you're going to get more strength out of that. It's almost going to turn it, like the part that bends is a lot shorter, and the length of these things is drives, and I think it's like the square of the length. Okay, and so they're going to fail laterally and fail by bending rather than failing by direct compression of the material, which we said can take a huge amount. You can demonstrate this behavior by compressing a plastic ruler. That's the best thing. Take a ruler, push down on it, or any other slender object. And then take a ruler and see if you can actually get the molecules to line up, and see if there's a moment where it's like, no, it pops, and be like, hell yeah, we need to design for that. Cool. So when lateral bending occurs, we say that the column has buckled. And then the other thing to keep in mind as we dive into this is, let's say the column starts to buckle right away. You already kind of deflected a little bit, and so as you put pressure down, it's deflecting more and more. But like, you should be able to increase the pressure. It's not just going to be linearly like it's going to be a plastic. And that brings up the other main aspect of material mechanics is linear elasticity, meaning that, when we put force on things, they're going to act as springs. Like, the molecules are going to, very much act like linear springs. And it's linear because those distances are probably very small. Molecules are just shifting and then getting into like a more, like, almost cold forged location. Yeah, I don't know if it's, I wouldn't say forging because that's deformation. But I mean, as the molecules are shifting, then you have that much play in the system, and it's not just a constant force cause constant motion. It's like you have to put more force to get more deflection, and then more force to get more deflection. And the whole idea of material mechanics is the material's hella strong, and you can put an amount of force where if you back that force off, all the molecules go back to the identical shape that it was. And I think that's very good to keep in your mind, like just identical location of molecules up to the materials. And I would just call it strength. That's the first value that I would just always have in my head. It's like, hey, that's going to be the strength of the material. And that's where things are going to yield. If you go past that, you're just permanently turning your project into like bent Play-Doh. You know what I mean? Or yeah, it turns into a plastic and it's permanently bent. Now it's going to rebound quite a bit, even if you just go a little bit past there. But the deflections can be, I mean, the amount that we're bending this. Well, I shouldn't say that. In axial compression, like the amount that you'd actually change the length is going to be very, very small. Bending's the opposite, because every little, from the derivation, like every molecule is changing the angle of this. So you don't actually get a whole lot of distance, like a separation of distance between the molecules, but because every line of molecules is separating and then crunching, deflections just add up wickedly, where you can get something to just deflect a whole lot without reaching that permanent plastic range. And then even when you do pass that force of permanent plasticity, if you just pass it a little bit, most of this will go back to its original shape, and it'll just be maybe bent a little bit. The main thing to keep in mind, though, is a lot of materials like steel, like ductile materials, man, you can bend them huge amounts before they might break in some cases. Some designs are just very rigid and brittle just by their structure, where if a car goes over, you might not see bending, and then just all of a sudden you have a bridge failure. You know what I mean? That could be a steel bridge too. You know what I mean? Does a steel bridge with a lot of supports, like pin connections and all that, you might not get, you might just get instant failure, just because like you have a lot of rigid connections that are, like not, you can't bend them a large amount. It's not designed to bend. Hell yeah. All right, we need to move on. But that's kind of what I would sometimes just get into spending half hour talking about when it comes to just introducing material mechanics every chapter that we go through. All right, so when lateral bending occurs, we say that the column has buckled. Under an increasing axial load, the lateral deflections will increase too. So that's the important thing. Increased load, increased deflection. And let's just pretend it's linear, until the equations tell us otherwise. That's a safe bet. I don't know. I mean, I think it's just good to say that if you increase the load, you'll increase the bending, but these are still static problems. You know what I mean? I put load, I see a bend, and then everything is stopped. Put a load, we're not worried about moving. All the loads are applied so slowly that the dynamics are not taken into consideration. Cool. So the phenomena. Okay, did we read everything? Under an axial load, the lateral deflections will increase too, and eventually the column will collapse completely. The phenomenon of buckling is not limited to columns. Buckling can occur in many kinds of structures and can take many forms. When you step on the top of an empty aluminum can, the thin cylindrical walls buckle under your weight and the can collapses. When a large bridge collapsed a few years ago, investigators found that failure was caused by the buckling of thin steel plate that was wrinkled upon compressive stresses. Buckling is one of the major causes of failure in structures, and therefore the possibility of buckling should always be considered in design. So we have buckling and stability. To illustrate the fundamental concepts of buckling and stability, we will analyze the ideal structure of buckling model shown in figure 12.2a. In textbooks, if you ever see a figure, just immediately go to the figure, kind of wrap your mind around it. So we got 11, and I said 12. 11.2a, buckling of an idealized structure consisting of two rigid bars and a rotating spring. And just go through and just kind of identify things. This is figure A of figure 11.2. We have a pin connection. We have a roller. All force will be in between this pin and this pin. We're going to assume that it bends out. And in this model, this pin is a free connection. So if we did not have this spring here, it would require no force to just have this thing collapse. You know what I mean? But we need this spring, and so if we push down a little bit, it bends a little bit. Push down a little bit more, it bends a little bit more. Hell yeah. And then anytime they're going to use moments for a free body diagram, I don't know. I think it could be really good to even just put 2 applied forces, pretend like you welded a little bar. So this thing is going to be spinning this way. Pretend like you just welded a little bar at a perpendicular, and you got, you're turning it like a steering wheel this way and that way. And that's what you're trying to do to that thing. All right, hell yeah. And then the other thing, I think it's difficult with these free body diagrams, because what do we have here? I'm pushing down, I know that, and this is a statics problem. So I have a rigid chunk of material that I'm pushing down right here. Now this pin is going to have, now is this pin a 2-force member? Aren't the loads? I guess the loads aren't 2-force members on this one. Oh, this is interesting. Let's see. Oh yeah. See, I'm having even troubles. Just like I don't know if I believe this. You know what I mean? But well, this is interesting to me. I'm applying a downward force, and it's downward. I kind of struggle with statics. Be like, well, is there no force on this? You know what I mean? If I'm just applying a downward force to this system, is there? I mean, sometimes you get a leverage where if I put a bowling ball between 2 wedges, I'm putting a downward force. Well, not technically. There's a force of gravity through that bowling ball, but whatever that bowling ball is touching is at angles. So yeah, this is interesting. So yeah, I'm kind of having a hard time with this one. But downward force is going to be equal in the up direction. This is causing a moment. This force and this force is causing this thing to rotate. We observe that bar is not rotating. So that's how you kind of do free body diagrams, is I just take this bar and just pretend like it's floating in outer space. And then if this is the experiment on Earth, just mimic it in outer space. So I'm going to put a downward force. And you can imagine this is like a little jetpack. I'm going to put a little jetpack blowing that way, and it's going to force this down that way. I'm going to balance that jetpack with another jetpack that's blowing this way and putting an upward force that way. I think for me, that's just visually, I can really see that. And then this is interesting because I can't apply a moment at this roller. This roller can only apply a force that direction, but it can't do anything else. So yeah, so that's fascinating, because can't this pin also provide isn't this a pin connection where it can provide yeah, that's where I'm struggling with this one. But anyway, let's just say it is how it is, and I just don't fully grasp it yet. And maybe we'll just read the textbook. But if I apply a moment on this rigid body, I can, in this, like a rotating, it doesn't matter where I place that moment for a statics problem. If there's no motion, and maybe a dynamics problem too, but I mean, just for a statics problem, I could weld my little thing anywhere onto this rigid body and just apply that torque, and that's going to resist. So this force and this force are causing this thing to spin this way. This counter is causing it to be stationary. So that's what this spring is doing onto this bar. This spring is the same thing as a welded, something with 2 handles and someone like turning it and resisting this load and this load. All right, hell yeah. So I think we can move on now. All right, this is the idealized structure of buckling model. This hypothetical structure consists of 2 rigid bars, A, B, and BC. So we have this lower bar, AB, then we got BC. All right, now I don't have any water with me, so we just got to crush and then call it a video. All right, so cool. Each of the lengths are L divided by 2. Cool, they're joined at B, must be in the middle by a pin connection, and held in a vertical position by that rotating spring, having a spring stiffness. Cool. And what's the equation? Just in general, the equation for a spring is force on the spring is change in length times the stiffness. Because if I have a change in length of the spring, that's going to be in meters, let's say, and the stiffness is going to be force divided by meters. So a change in length times the stiffness gives the force. And those are another simple equation. I got force is related to change in length. You know what I mean? And stiffness, well, I don't even know if that's what they're actually saying by stiffness. But your spring constant, oh, so yeah, this is a different quantity. Sometimes you have a force and a change in length. So I'm glad I actually went over that, because this is a new one to me. This is equating moment and the angle that's being caused. So if I apply this moment at B, or this spring is seeing if this spring is applying a moment, because we're putting an equal and opposite force into the spring. The spring is providing this force to counter. And as we're pushing down, I should get this right, it's pushing this bar this way. So the spring actually, it kind of, it wants to pull it back. So the spring is probably getting unwound, and then the spring is pushing. I really can't tell if they even drew the spring right, But anyway, so hell yeah, that spring is trying to be a restoring force. And it's going to be a measurement. The spring is going to have a measurement of causing a moment, which is force times distance, or just that quantity of force times distance. And that's where you can get into the idea of just welding a small little perpendicular rod with two handles and applying equal and opposite forces, at that distance. And that's a very good way to just know, hey, it's a moment is just a couple of forces, equal and opposite, separated by a distance. Booyah. And then so instead of force is equal to change in length, and instead of force being proportional to the change in length of the spring, we have the moment is proportional to this change in angle. So hell yeah. I could quit the video and be like, didn't know that. Never really paid attention to that. I probably just saw this. I don't like Greek letters anyway. But we got beta R. I don't even know what the R stands for. But the general relationship for rotational spring, there's what the R stands for. R is for the rotational spring, is the moment is equal to the stiffness times, and then the angles are always going to be in radians. And radians is dimensionless. Moments is in, and you don't have to think of this as dimensionless, but we do need to cancel the units of radians. If you could think of it that way. So this is going to have units of 1 divided by radians. The radians cancel. But this has units of force times length, like Newton meters. That's torque. So this has to be like Newton meter per radians. And that's good. For any of these constants, and especially a proportional constant is always going to be and it's the slope. You know what I mean? This is a y equals the slope times x plus it goes through the y-intercept, y is equal to mx plus b. That part is 0. So, and then I want to make a lot of differential. That's the first time I stuttered, so that's pretty decent. So we're doing pretty good on that. I'm trying to keep track of that because there's no benefit to me. And it chills me out if I catch that. So, hell yeah. I want to make some videos. And it just means I just got excited, kind of. Else, it just means that I'm struggling. Anyway, so, yeah, so the slope is differential. Even if the equation is linear and you have a constant slope, it's still a differential. A ratio between, a conversion factor is a differential proportion and can't be considered like a differential equation. Even though you Google it, you'll get kind of a mixed review on that. So, but I think learning differential, integral calculus, differential calculus at the simplest level is the most important tool to build from. Because if you don't know your bases, if you have to start at integration of x squared, I get that. But, I don't know what the integration of a constant is or something. I don't know. So it's very useful to take things down to their base level. But this, again, another linear equation where this is your proportional constant. This isn't going to change, and the reason it's not, because it's linear. And it's just spelled that way. This should read like a differential equation. You should have this as a differential where that differential is a constant. And then you can say that if I change theta, then the moment will change linearly. And that's kind of interesting because that kind of helps me out. I'm just going to move on. Okay, where m is the moment acting through the spring, beta r is the rotational stiffness of the spring, theta, is the angle through which the spring rotates. Thus, rotational stiffness has units of moment divided by angle, such as, I didn't bring my ice water, and I just thought we'd crush this out or something. Pound, inch, radians. But it is good for me to try to change my vocal tone so I'm not so harsh on my vocal cords. But damn, ice water is really good. All right, you see those units that they cancel. We said force, length, divided by radians. The analogous relationship for a translational spring. Yeah, and then we just talked about that analogous relationship. Force is equal to change in length times a constant. And this is their constant. I would call it K. I don't know why they use beta again, but whatever. Where F is the force acting on the spring, beta is the translational stiffness of the spring or spring constant, and delta is the change in length of the spring. And I think this is lowercase delta. I don't mind warming up to the Greek letters because that caret is the uppercase delta, and I shouldn't call it caret, but whatever. I don't even know if it is. No, a caret is like the thing above the number 6 on a keypad. So if I'm calling delta a caret, I think I'm actually calling that wrong. I think someone called me out on that. Anyway, thus translational stiffness has units of force divided by length. Yeah, so if we have translational stiffness, this is rotational stiffness. All right, I think I'm good on terminology. Translational stiffness, the spring constant, is pounds per inches, because then if we multiply by a change in length, we get the force. And yes, a change in length in a spring equals, you must have put a force on it. Cool. All right, so this idealized structure is analogous to the column in figure 11.1a. What up? Cool. Okay, there you go. Yeah, because this 11.1a, we're going to get a bunch of ones. This is just 2 pin connections and a roller. You're going to get more. I mean, like, why would you build a building like that? You know what I mean? So this is just kind of the simplest, maybe one of the simpler cases, or the simplest. The idealized structure in figure 11a. Because both structures have simple supports at the ends and are compressed by an axial load P, however, the elasticity of the idealized structure is concentrated in the rotational spring, whereas a real column can bend throughout its length. Yeah, but, you know what I mean? When I go design, like, you know what I mean? Like, if you're designing a bridge, where if you just put the load in the middle, cool, you're going to have shear forces and the concentrated load, but you could just assume it's pure bending. I don't know, you know what I mean? So you just have this idealized thing where it's just like, I'm just making pure bending. So that's what we have. And this one is, let's read it again. So we have, however, the elasticity of the idealized structure is concentrated in the rotational spring. Yeah, just right. The only thing that can take a resistance in rotation, which is we call the moment, which provides static equilibrium, is that spring right in the middle. All right. I'm not going to last very long. Cool. In the idealized structure, the 2 bars, we need to see how far we can get. Yep, I think we're just going to do the setup on this one, because I just need more ice water. Unless I want to do this in 2 parts, catch you on the flip side. Right, hell yeah, I got some ice water, and we're 30 minutes in, so we're doing pretty good. I just want to actually get to the part that I'm confused at, you know what I mean? So, hell yeah. So now, let's see, are we to here? Who cares? In the idealized structure, the 2 bars are perfectly aligned, and the axial load P has its line of action along the longitudinal axis. And you know how we kind of just looked at the diagrams and kind of made an assessment, and now we're just reading, we're almost kind of reiterating what we were contemplating too. So, hell yeah. But in this, we're going to get to a place where the equations, we're just going to be like, I don't know. And then we're going to read it and still be like, I don't know. So, consequently, the spring is initially unstressed and the bars are in direct compression. And that's the deal. Yeah, those bars are in direct compression, but under this thing where you have a spring is, we're assuming just a small little offset probably, or however you want to do that, where any sort of downward force is causing that spring to deflect, causing that angle to form. Now suppose that the structure is disturbed by some external force that causes point B. Okay, yeah. So I guess they have to do two things. One is they have to say 11-2A in figure 11-2A, and we're not doing good justice. Yes, if it is set up like this, you can put a load, and technically it's just going to maintain its upright position, and it's just going to balance one on another. It's unstable. It's an unstable balance point, and all of a sudden it might pop out to the side like that. And so now we're going to read about... So we're going to read about a lateral disturbance. Now suppose that the structure is disturbed by some external force that causes point B, to move in a small distance laterally. The rigid bar rotates through small angles, delta, and a moment develops in the spring, providing a restoring force. Brings it. And then so the direction of this moment is such that it tends to return the structure to its original straight position, and therefore is called a restoring moment. At the same time, however, the tendency of the axial compressive force, okay, see I spaced out, but cool, we have that force straight down, is to increase, increase that force, increase that angle theta. That's kind of what they're saying. Thus, these two actions have opposite effects. The restoring force moment tends to decrease that angle, which we're calling the displacement. So this displacement is this angle. And then the axial force tends to increase it. Now consider what happens when the disturbing force is removed. If the axial force P is relatively small, the action of the restoring moment will predominate over the action of the axial force, and the structure will return to its initial straight position. Okay, so this is saying that you can put the force... Okay, yeah, so I finally understand at least that part. If we set this up as an experiment, just kind of a fun little thing to do, maybe if we push down and nothing happens because, there's a lot of balancing points, but if it's a true, pivot, and we actually give it a tiny bit of deflection to start out, we're going to say that if we put a tiny bit of force, we're going to get a tiny bit of angle. And I don't know, Maybe this isn't linear. No, it is linear, because we just said the moment and the stiffness and the angle is a linear relationship. Cool. But what it's going to say is that as we push down, this moment is going to cause a restoring force. But check this out. At a small angle of this bar, these forces, P and P, are relatively in line. So even if we have a large load, we have a small distance from this line of action to this line of action. So the moment caused by this column is small. And this is an idealized situation. You ever go into a building where you're just like, oh, look at that. Look at that column. I think something's happening in that one. That's where these deflections are, sometimes beyond observable. And so, and the column's ready to buckle or something. So just keep that in mind. But because these lines of action are really close together, potentially, you can have huge loads in the column, and the restoring force, and then because those loads are very close in line of action, their tendency to try to rotate this section of the column is relatively small. Even if the loads P are huge, again, that distance is small. And so, but it is there. So even in a column in a building, it might be, buckled. It might be doing this. It might be bowed out in a linear, elastic way, in a way that, we just know is happening. But the material itself is providing the restoring moment. And we're just idealizing the material capacity to resist bending as this spring. But it is. If I take away the load, the bar goes totally vertical. And then what this next segment is going to talk about is like, yeah, you can get to a point where the angle, and this brings up like the capacity of something. This happens a ton in physics. If I have a car on dry, sunny pavement in the summertime, or I don't even know why I said that, but and then the tow truck comes and then just like tries to wrap a chain around it and just drag it sideways, just sideways down the road in like the worst possible way. The car is going to slide across the pavement because of friction and the weight of the car. And so when the winch is being applied and the mechanics are being turned on and the battery winch is being done, you're applying force to that car, but with a little bit of force, you're seeing no movement. So in that case, no movement, and force, you're going to build that force until you reach a maximum force, and now the car is sliding. Okay, cool. Had your winch not been strong enough and you apply this force to this car and you don't see any movement, the car's not sliding, then you go to you take away the force, you go the other direction on the winch and you say my winch isn't strong enough. That car goes back to its original location. It actually didn't move, but I'm just bringing that up as an analogy in physics. So we're going to say, hey, this member is a spring, and we're going to, just the column itself is going to have properties that can restore force like a spring, and we're going to see that internally. But we're going to right now just assume that a column is this pivot at B, and we have installed the spring in the column. But the analogy is this spring can only take so much force before it's sprung. And you can do this just with household springs. Go make it linear elastic. Pull on it, see the force, and then let it go, and it should go back to the same shape. But we all know that if you pull too far on a spring, well, it's sprung. And at that point, it can't go back. So that's the same thing with this scenario. We can spring this spring so far, I think it just reaches a maximum where maybe this moment can only provide a restoring force. The spring is only strong enough. But then when we apply this force down and this position B gets swept out because this bar becomes more horizontal, this distance gets huge between this axial load and that axial load. And then so there's a point where the spring, the moment at B, the restoring moment of the spring and its properties can't take no more. And then so the force P dominates and the spring, I would say, quote unquote, breaks, it has an upper limit, and and just gets swept the other direction, because any increase in this angle, and it might be like right now, like this thing right now, maybe the spring is all it can take. And then you can just see that if we push down farther, this angle is just going to easily get bigger. And even though it's a linear relationship for what that spring can take, at some point that spring's going to reach a max and say no more, and then so this whole thing's going to collapse. And hopefully that's kind of what they're talking about. So we're applying a load and removing the disturbing force. So we're saying if we apply a small load at P, cool, the action of the restoring moment will predominate. And I'm just going to say again, the restoring moment has a maximum. But it's just like friction. It's like if you're below that maximum, cool. And then so that's going to predominate, and the action of the axial force and the structure will return to its initial straight position. Yes, the restoring moment will predominate over that axial force P, and it'll return to its initial straight position. Under these conditions, the structure is said to be stable. However, if the axial force P is large, the lateral displacement of point B will increase, and the bars will rotate through larger and larger angles until the structure collapses. And I think we did a better job of explaining that because that spring got sprung. Spring only has a max strength, and we sprung it. So under these conditions, the structure is unstable and fails by lateral buckling. And so that's going to be this P critical value. So critical load. The transition between stable and unstable conditions occur at a special value of the force known as the critical load, denoted by the symbol P critical. We can determine the critical load of our buckling model by considering the structure in the disturbed position 11.2b. That's just going to be that middle diagram. Cool. And so right here is where we're at, and investigating its equilibrium. First, we consider the entire structure as a free body and some moments about support A. This can be the bottom. This step leads, or I don't know. Let's find out. Where's support A? Yeah, right at the bottom. Hell yeah. Yeah, so we're going to do the, okay. Yeah, so right here, this axial load goes through A, and we're going to do the full free body diagram. So we're going to take both bars together and see that if we have a downward force at pin A, we must have an upward force to balance. We have no lateral forces, so there's no lateral forces at A. Therefore, there's no lateral forces at C. That's a global equilibrium. I always forget to do that. It's just like, hey, is this what is this structure touching? In its most basic, it's touching this pivot, and it's touching that pivot, which is a roller, or you just say it's touching that roller. So you're going to chop that out of outer space. Okay, so we're done with that. So there's an upward force at B, no side forces. There's an upward force at A. So therefore, if we do a free body diagram just on this BA, which they didn't do, we will see there's an upward force on A, there must be a downward force on B, and therefore equal and opposite. If there's a downward force on this member B, there must be an equal and opposite force on member B. Or on this upper member at that point B. The other way to think of it, I like to do the demonstrations where you take two socket wrenches. So you take two wrenches with the holes in them and then throw just like a socket in there as a pin. And then I'm going to be, so this one gets pushed up. So I'm pushing up at A, and then something has to push down at B. And that's technically like something as in, something material, and that could be the pin. So the pin pushes down at B, and if the pin is pushing down at B, it's also bummer. So this is pushing up, that's pushing down. I don't think anyway. I'm so bad at this equal and opposite stuff, man. You know what I mean? I'd have to just do another. Sorry, I got a little, because it seems like, well, if I push down on the pin at B, pushing down on this member, balancing this upward, why isn't that pin pulling down right there? It's like, well, because of, the other thing is because, hey, I'm pushing down for sure on this member, and I'm not seeing this chunk of mass go in that direction. And so if this is the only point that's actually pushing up on this chunk of mass, it has to be up. Same thing here. If I figured out that this chunk of mass is being pushed up at A, the only point that can actually push down to make a balanced thing is at point B. And I'm just going to leave it at that, because else I'll lose my free mind. But that's a good place for me to go study up on. You know what I mean? Take a couple socket wrenches and then do the pin and then see what the hell. I bet you we could do it. What the hell? Yeah, if this is a wrench and I'm pushing up, something's pushing down. And if I'm pushing down with the pin is pushing down. Cool, at point B. Oh, that's the thing. The pin is the third chunk of mass. And I love pins because they are chunks of mass. And they're just smaller, and I think they're easier to deal with. Because, like, hey, if I am the person pulling down on this pin to try to keep this member from moving upward, cool. I'm pulling down on the pin. Something is pushing up on me, but I'm pushing down on this member. And so to balance, yeah, how do you say that? Oh, that's super interesting. But just on this pin, I'm pushing down on it, And so, and having it offset. Let's say this member is way out to the side, and I still have an upward force at A, and I'm trying to balance it with a downward force at B, or even just with this angle. Let's say A and B are the only things. Bummer. Yep. That's not helping. Yeah, because minus the spring, I'm going to pull down on this pin, and yes, the whole thing is just going to easily collapse. It's unstable. Yep. And so upward force at A, this is, if you see it, cool. Man, I need to study more. But I think equal and opposite forces are the trickiest things, because in lecture, you can just be like, oh man, I can't follow this because I'm just losing my mind. But hell yeah, upward force at A, downward force on this member. I guess equal and opposite, so that must mean I'm putting an upward force on this member. And that's because the upward force here, it's the global equilibrium, and then taking sections, you know what I mean? It's just like, well, this upward force don't go away, you know what I mean? It's still, so I'm going to leave it at that. That was an awful 10 minutes. Okay, sweet. So we can determine the critical load of our buckling by considering the structure in the disturbed position 11-2B and investigate its equilibrium. First, we will consider the entire setup as a free body and sum moments. We're going to sum moments about support A. Oh, that's interesting. This step leads to the conclusion that there is no horizontal... Yeah, because there's that downward force at P that goes through A. No horizontal reaction at support C. And where the hell is support C? Yeah, right here. So yeah, there's no horizontal... Yeah. This force goes straight through A, sum the moments at A. There's no lateral force. Well, if we sum moments at A, yes, there's no force up against this wall at roller C. That's summing moments at A. That makes sense. And we're taking that whole free body diagram, which they don't show. They just show the other portion, which we'll get into. So now it says second, we consider bar BC as a free body, and note that it is subject to the action of the axial force P and the moment B in the spring. The moment B is equal to the rotational stiffness, beta R, times the angle of rotation, twice the angle of rotation. So 2 times the angle of rotation of the spring. And, cool. Do I understand why? 2 times the rotation. This is because these 2 angles or whatever. See, I'm already lost, and that sucks. You know what I mean? So that's a place where I don't. Is it because we have to? This spring is getting twice as sprung from both. You know what I mean? Or yeah, how's that? Or is it? Oh man. Yeah, this tripped me out. Okay. Well, I mean, we know this. Well, let's work a little bit ahead, because what is this moment equal to in this equilibrium? We have a couple, that's P, and then we have the distance between this. This is L divided by 2, so I want to know this distance, which is it's the sine of the angle, you know what I mean? So whatever L divided by 2 is, and this is where I sometimes need to actually have a teaching moment. So this is going to be a triangle. This length could be like 10 inches. It doesn't mean this length of, let's say this, stuttered like 3 times. So let's say this length is like 2 inches and this length is 10 inches. This length is 20% of that length. So when we say this is the force and this is the force, and we have this distance separating them, oh damn it, in this case the length actually is the actual parameter. Sometimes when you work with vectors, it's just the shape of the circle mimics the shape of the vectors. But no, in this scenario, this is actually a length. And so that's going to be L divided by 2 sine of this angle. And we're going to say these angles are really small, and the angles are in radians. So sine of a very small angle is just the angle itself. So this length is going to be L divided by 2. Not sine of the angle, but just angle. You know what I mean? So it's going to be L angle divided by 2. And that is going to be the moment right here. My bad. The length is L theta divided by 2, but we have to multiply that by these equal and opposite forces, because a moment is two forces separated by a perpendicular distance. Perpendicular distance is that L theta divided by 2. And so now we have P critical, or just P, just the axial load, or the moment at B is P L theta divided by 2. So let's see what they even, you know what I mean, are they doing something different first? Because they're saying that the moment at B is 2br theta. Since the angle is a small quantity, the lateral displacement of point B is theta L divided by 2. So that's the lateral displacement. Yeah, we came up with that one. L theta divided by 2. Or L divided by 2 times, you know what I mean, sine of that angle is just L, you know, theta divided by 2. I would say it that way. But anyway. But actually, sometimes I do say radians times radius is arc length. So that's what you see here. Radians times radius is arc length. That's a really good thing to say. Radians, this is the radians, times this radius, which is L divided by 2, is this arc length. And that is going to be an arc. But when that arc is really small, it's almost just a straight shot. And so it's that proportion of a right triangle. So that's the small angle. And that comes up tons in this book. Okay, so therefore we obtained the following, but how does that get us to here? Let's go back and look at where they used MB as a stiffness equation. Because they were saying right up here, haven't they used that yet? Holy Toledo. Didn't they just say that M... Yeah, right here. We have moment is equal to BR theta. The general relationship. Is there like twice the moment happening because of this shape or something? Is the other end of this column driving this to be sprung? Is that also what's happening? I'm kind of getting tweaked out on that. I don't know, man. So, yeah, that's just one of the things where it's just like, darn it, they're not explaining it. And that derails me for a little bit, you know what I mean? But I think we just need to move on or just read it one more time. So the moment B is equal to the rotational stiffness times the angle of rotation. But it's just 2 times the angle of rotation. Since the angle... And I don't know where they're getting this equation, but whatever. Maybe just because, yeah, because just the geometry, there's 2 of them or something. And you're getting double sprung. You know, it's almost like the leverage of 2 springs or something, or twice the force on 1 spring. I'm just going to assume that's the case, and I just don't fully see it, but we got to move on. Since the angle theta is small, then this angle, the lateral displacement of point B is this. Therefore, we obtain the following equation of equilibrium by summing moments about point B for bar C. Now, let's just do this. What's the sum of moments about point B? We're going to have P times that distance, which is theta, L divided by 2. So that's going to be a right-hand rule, a negative torque. So we have negative P L theta divided by 2. MB is a positive torque, and they've already said that's going to be 2 beta R theta. So that's what we have. So we're going to have negative P, and then that distance, theta L divided by 2, and that's going to be a negative moment. And then we got MB, which is 2 beta R theta. Because we have a theta here, and this is 2 beta R theta. They do a lot in this textbook. They just jump from there to there, and sometimes it's hard to see. But now we have, oh yeah. And so here's our, so one of this solution is that the angle is 0. So even if we're putting an axial load on, there's a chance that it's just rigidly attaching, well, no, let's see what this one says. The solution is when the angle is 0, which is a trivial solution. It merely means that the structure is in equilibrium when it's perfectly straight, regardless of the magnitude of force P. Yeah, so we have that kind of just instability of this setup where we put a load at P. Maybe it's just all an axial compression, and it's just compressing like an accordion, and none of it's getting popped out the side, activating that spring. Okay, hell yeah. So, so that's the trivial solution. A second solution is obtained by setting the term in parentheses equal to 0. Yeah, I love this, because I can follow it. When we have a product of two things is equal to 0, well, it's either when one of them is 0 or the other. It can be when they're both 0, but the cool thing is if one of the products is 0, the other one can be any angle. So when I set this equal to 0, hell yeah, that's what we're going to do for this one. Setting the term in parentheses equal to 0 and solving for the load P. And then we're going to call it the critical load. So if this is equal to 0, I'm going to get like that to the other side. The equal sign just goes right here, positive, positive. I'm going to bring the 2 up, so we got 4BR. I'm going to divide by L. So we got 4BR divided by L. BR is the beta rotational spring stiffness in that spring. At the critical value of the load, the structure is in equilibrium regardless of the magnitude of the angle, theta, provided the angle remains small, because we made that assumption. Yeah, so I just spaced out, but yes, the critical value, this equation only works when angle's small. If it's not small, you got to throw it back in. And there's plenty of problems where, yeah, you could do this with a structure that's hella bendy, and that angle's going to be hella, and you got to just remember that. And so that's that. Now that's your, I'm just telling you now. Tell you. So from the preceding analysis, get some water. We see that the critical load is the only load for which the structure will be in equilibrium in the disturbed position. At this value of the load, the restoring effect of the moment in the spring just matches the buckling effect of the axial load. Yeah, so this is one where it's like, hey, it just matches. This is same thing as friction. Like if you push the car sideways, cool, the friction is pushing back kind of at the same force. You could think of friction as not a driving force, just a capturing force maybe. I made that term up, capturing, just now. So therefore the critical load represents the boundary between the stable and unstable conditions. Or maybe I'm saying that wrong too. So so we are saying that there's a, I don't like this at all. Okay, so I'm kind of, yeah, so somehow in this equation, we're finding when, yeah, we have a moment that's a function, yeah, that's right, I totally forgot, is because this moment is a function of the angle, where this moment is 2b, and they shouldn't have just jumped steps like this, because this moment is 2br theta, and you can see that this moment right here is 2br and then this theta, and then the axial load, no, I'm sorry, the moment caused by the axial load, because you're creating that shape, is over here. And this is the negative moment that's causing it to fail. So if we look at the positive or negative on this bar, if I put a moment at B, so if I'm summing moments at B, and I do the right-hand rule this way, that's going to be a moment to make this thing go flat and go pancake and buckle. So that's going to be a negative moment. So when the negative moment is kind of dominating, and then the positive is trying to restore, then you're going to get, yeah, so maybe a collapse. So we can take a look at that equation. So this equation says that, and I wish they didn't just separate this right away, because you have 2br theta right here, 2br theta, and then minus PL divided by 2 theta. And what you'll get is if the angle is just a little bit small, just a tiny angle, this negative P, again, won't drive. It's not going to be that big of a deal. And then the moment is going to be 2BR theta. Well, the restoring moment just has to match that. And, oh, that's so fascinating. So I'm kind of at a loss from, I get how if the angle gets big, this moment gets big. But we're equally... Oh, yeah, that's why we need to go to this graph. And I don't think this is trivial at all. You get this to be the line where you're reaching that balance of equilibrium, where you have... Oh, yeah, and it is a statics problem. This is so fascinating. No, this is when P critical, you can move that thing all along here and it will be perfectly balanced. So, and so this is force. So this is, yeah, this is why I'm making this, because, this is, stuff like this, for whatever reason, I just start to make up stuff in my head or something, and I don't know how to catch myself. But this is a graph of changing the angle and the force applied. So let's start at the very origin. Apply a little force, nothing happens. No angle, right? Because I would be going out to the side. Apply a little bit more force, nothing happens. So this actually says this P critical is the position where we have to apply enough force for then it able to move laterally. And then, and if we apply a force bigger than that, it's just going to buckle. You know what I mean? So this is your buckling region. This is the force critical that actually... Oh, and then, oh, bummer, dude. Actually, I fully don't understand this, because it seems like if you push just a little bit of load down, you're going to get a little bit of an angle. But where's that line on here? I do not see that. So yeah, there's something fundamental that I'm not picking up. But that's all right. That's why we do this. We read through, and if you can see it before I do, hell yeah. All right, so So from the preceding analysis, we see that the critical load is the only load for which the structure will be in equilibrium in the disturbed position. At this value of the load, the restoring effect of the moment in the spring just matches the buckling effect of the axial load. Therefore, the critical load represents the boundary between the stable and unstable conditions. If the axial load is less than P critical, the effect of the movement in the spring predominates and the structure returns to the vertical position. After a slight disturbance, if the axial load is larger than P critical, the effect of the axial force predominates and the structure buckles. So if P is less than P critical, the structure is stable. But still, in their diagram, you still have a little bit of P. You still get an angle to form, with theta. So I don't get how that's not representative on that graph. But if P is greater than P critical, the structure is unstable. So from equation 11.2, we see that the stability of the structure is increased by either increasing its stiffness or by decreasing its length. And that makes sense. If we decrease its length, that leverage, so if we do start to get this angle to form, this length is going to be a lot lower. And then so this couple of forces, this distance gets less. Hell yeah. Later in this chapter, we will determine critical loads for various types of columns, and we will see these same observations. So yeah, they lost me, but whatever. Summary. Let us now summarize the behavior of idealized structure as the axial load P increases from 0 to a large value. Hell yeah. When the axial load is less than the critical load, when P is less than the critical but greater than 0, the structure is in equilibrium. When it is perfectly straight. because the equilibrium is stable. And so this is when the structure is totally straight. You get to a point where P is less than P critical. Because the equilibrium is stable, the structure returns to its initial position after being disturbed. Oh, I finally understand that. Okay, I finally get this whole, oh, this is crazy. Okay, so, yeah, huge, like asterisks on the page. So this would be a good one to experiment with. And the funny thing is I probably made a video on this, or actually talked my way through it, and probably already posted it, and I'm just doing the same thing, and I'm running into the same mistake, and I just didn't read far enough, but it was right there that was the aha click, and it's just like, okay, so here's the deal. If I set this project up where I have a restoring spring, and I push down with a force P, sure, I'm generating this angle, and P is going to be balanced by this force. And so when I let go of P, it's going to restore, and therefore the angle is 0. And then, but what's going to happen is if I push down far enough past P critical, this spring, that's the thing I'll have to go work on. What in the equation causes this spring? Like, what are they saying? Why is the spring buckling? But because it gets past a certain point where the spring probably actually, even if it doesn't like get sprung, it actually can't restore, and it'll actually make it collapse even farther. I think it has to be part of it. Because at no point do they use my analogy of saying like the spring broke or anything like that. It just gets past like a critical point where it just like collapses in. And maybe that's the case. I'll have to look at that. Yeah. Well, let's say you got, I don't know, I mean, this spring still is supposed to apply a restoring force this way as the angle increases. And so the angle is increasing. But yeah, I guess at some point they say the force well, don't they actually say if you get past this force critical, then when you let go, it actually just doesn't go back? It's like stuck or something? We need to read more about that, but I think we're close. Okay, so when the axial load is less than P critical, the structure is in stable equilibrium when it is perfectly straight. Because the equilibrium is stable, the structure returns to its initial position after being disturbed. Okay, yeah. See, I read that, and then I thought I had the aha moment, and then I went back and we just butchered it again. Okay. So the whole idea is you physically disturbing this point B. And so if I push down on P and then I pull point B just a little, I get it. So it's really difficult, especially when you have a moving system, of like what's a force on a moving system, because it seems like if the system moves, maybe that force like reduces itself. So I'm gonna hang a sandbag from point C. So it's gonna be in this shape. It's gonna be disturbed. I'm gonna hang a sandbag from point C, just a light one, and it's gonna maintain this shape. And I'm gonna say this thing will like only when this angle gets to be hella out here will it collapse. Okay, so I think what they're saying is if the sandbags hang in from point C, we got that load on it, and then I disturb this way or that way. Both ways. I can push this column in, or I can pull this column out slowly, and then I can let go of it slowly, and it's going to return to this equilibrium position. I think that's kind of what they're saying. Then you get to a point where if this load is at a critical value and I start to pull this spring that way, the load will be greater than the spring can handle or something. And so, man, I still don't understand the experiment that they're doing. But I think we're close. We're closer. I knew this one was going to be tricky. That's why I wanted to do it. Let's read it. Every time I read this, it feels like I'm getting it and then go back to be like, nah, that's not what they said. Because the equilibrium is stable, the structure returns to its initial position after being disturbed. Okay, so it's disturbed by a force? Is that what they're saying? When it's disturbed by this load P that's less than critical, that's the disturbance? Maybe. And when you, after you release it, they just need more words here. This sucks. Thus, the structure is in equilibrium only when it is perfectly straight. Yeah, is that what they're saying? Okay, so, yeah, we talked about that, how the structure, if it's loaded, it's like balancing just in an unstable position. But they're saying that there's a critical load where it becomes buckled or something. So when the axial load is greater, when the axial load P applied is greater than the critical load, the structure is still in equilibrium when theta is equal to 0 because it is in direct compression and there is no moment in the spring. But the equilibrium is unstable and cannot be maintained. The slightest disturbance will cause the structure to buckle. That is fascinating. That's actually blowing me away right now. And it's, you know, you got the free body diagram, you know, that should explain it. But yeah, I mean, essentially, you know, it'd be good to throw some numbers with this because I could have a huge load here and just displace it just a tiny amount. But it has to, oh man, doesn't it have to be, but it's saying any tiny amount. There's just a critical load where any disturbance is going to cause it to buckle. And that's where you're up here. You're applying such a load that if you disturb it one way, okay, so that's where this graph at least understand. If a red line is not at that location, it will fail. You know what I mean? So I can't load it into this high zone and then move that point B just a little bit one way or the other. It's going to totally collapse. But it has to be related to the fact that that spring can only take a maximum amount. I wish they talked about that more. So at the critical load, the structure is in equilibrium even when point B is displaced laterally by a small amount. So yeah, if you're at that critical load, yeah, it's like just perfectly neutral. Like you push it over, there's no restoring force. It's just weirdly neutral. But this is small amounts. I mean, this is linear amounts. The second you actually develop an angle, you're going to have it totally collapse. So in other words, the structure is in equilibrium for any small angle. That's really important to this, including theta is equal to 0. However, the structure is neither stable nor unstable. It is at the boundary between stability and instability. This condition is referred to as neutral equilibrium. The three equilibrium conditions for the idealized structure are shown in the graph of axial load P versus angle of rotation. So I guess this whole stable part is like, cool, you applied a load, you know what I mean? We're not supposed to, you know, it's supposed to be balancing anyway, but then we move B to the side and B comes back. You actually, that also shows that I can't apply a low load and then move point B and then let go of point B. And, okay, so that makes sense. That means that this moment is a, yeah, it's like always dominating. So I think the biggest thing that that I said was if you apply a small load P, you get a small angle? I don't think so, not in this one. They're saying this thing is perfectly vertical, and they're saying if you apply a load and then you go move B laterally, and does that make sense? Okay, I think that makes sense because the force in the spring is a function of you moving this force laterally. And so that's what they're showing. They're saying you put a spring on this that's pretty friggin' stiff. Oh, okay, I think doing problems to the extremes is really good. I'm just going to say this force P is pretty low. You know what I mean? Even if I have a bag of rice and I got 2 sticks with, hinges, but this spring is just hella stiff. That's what I'm going to imagine. Hella stiff spring, a little bag of rice. This thing ain't, you know what I mean? And it's kind of balancing. That's another stutter. So it's kind of balancing on itself. And we talked about how this is stacked. It can kind of balance. We have a hella stiff spring. We got the bag of rice. Now I'm going to take point B and just move it a little bit. Like, I swear I would have expected this to happen. You know what I mean? Just looking at this picture, I see that. I see a very lightweight spring. The load is down and it's just in this position. But if that's the case where I do have a load and I pull this spring out and it stays that way, I know this is P critical. So this I wish they put an acronym here that says P critical, and I wish they put an acronym here that says P less than critical. That would have been very useful, and then maybe shown the spring to be like, hey, this is a stiff ass spring. Because hell yeah, bag of rice, perfectly vertical. I'm going to deflect point B. The spring is hella stiff. So just imagine that. It's almost like pulling, I don't know, like on a, but this spring is causing it's causing the moment to, and I'm sure this spring is getting double sprung based on both of those angles. I don't see it yet. I'll look at that. Some things I can handle and we can explore, but if I feel like I have no idea why it's a factor of 2. But there's 2 of these and they're at angles, so cool. But anyway, so if I just imagine a hella stiff spring with a little weight of rice on top of this system, and I pull point B back, it's going to take a lot of effort to pull that spring back, right? But let's say I'm able to. And then I'm going to let go. Yeah, it's going to return to this position. But there's going to be a point where it's just like, hey, let me pull this back, and then like someone add more bags of rice, hang it off point C. And then when I'm holding this, I'm holding a lot of tension but then people are adding weight to point C. And then at a certain point, I'm going to be like, stop. Actually, I'm not holding any more tension. And then that point B is just perfectly chill. And then what they're saying is now you can actually move this point B anywhere you want because there's a total relationship between the angle. Because this spring is a function of the angle, and this moment is a function of the angle. That is the hardest thing. I'm slowly understanding the beauty of the equations of physics. There's this one course in my town from the engineering program that's called like the physics with calculus, learning physics through calculus. But yeah, I'm just understood this from like right now. So I'm glad I'm doing this because I graduate, you go through this stuff and you're like, I don't know, let's just get to the equations and use them. And I kind of lost it already. Oh yeah. It's because when you increase the angle, both of these get increased the same amount. You know what I mean? And so if the spring, I just wish they said the spring, I don't know how they, well, no, the moment in the spring is a function of theta. And then the load and the moment, the distance is causing is also a function of theta. And then, but they're saying if this load is small, then this is going to be large. That's so fast. There's still, maybe I just ask too many questions or just expect too much. But yeah, because these two things are a function of theta, yeah, so fascinating. Yeah, it's so interesting. I feel like sometimes I got this one, and then other times I'm just like, nah, back to the drawing board. But yeah, that's an important aspect, that both of these are a function of theta, I'm pretty sure. All right, so let's go back to this summary. So we're doing pretty good. So at the critical load P, the structure is in equilibrium even when point B is displaced laterally by a small amount. In other words, the structure is in equilibrium for any small angle theta, including theta is equal to 0. However, the structure is neither stable nor unstable. It just can be moved around. And so this red represents equilibrium. So I can have this load P critical, and I can move that point B over there, and it's going to be a statics problem. It's going to take that shape, and we're going to be totally chill. But I can't have the force to be lower than P critical and then displace B and let go. It's no longer a statics problem. It's going to be a dynamics problem. It's going to do that. Same thing up here, but at this point, if the load is too high and then I displace P even just by a little bit, the whole thing collapses. And I think last time I read through this, I don't know if I did it on camera, I was just like, man, I actually need to set this experiment up. This would be a good one to set up and just to experience that collapse, because I don't see the collapse. I really don't. And I don't. I understand the collapse from the idea that a spring can only take so much force, but that's not even what they're saying. They're saying this spring is a function of this angle. And maybe it's not. Maybe this spring is only a function of small angles, and then you get to a point where, yeah, I don't know if there's unspoken stuff in this. I mean, I don't think there should be, but hell yeah. All right, so I think we just need to move on. I think we did a pretty good job. I think we understand this. These are the stable equilibriums. So the three equilibrium conditions for the idealized structure are shown in the graph of axial load P versus angle of rotation theta. The two heavy lines, one vertical and one horizontal, represent the equilibrium conditions. Point B, where the equilibrium diagram branches, is called the bifurcation point. The horizontal line for neutral equilibrium extends to the left and to the right of the vertical axis because the angle theta may be clockwise or counterclockwise. The line extends only a short distance, however, because our analysis, and this is where they explain it, is based upon the assumption that theta is small. This assumption is quite valid because theta is indeed small when the structure first departs from its vertical position. If buckling continues and theta becomes large, the line labeled neutral equilibrium curves upwards, as shown later in figure 11.11. Cool. I'm not going to, you can just imagine that. The three equilibrium conditions represented by the diagram of figure 11.3, that's this one up here, are analogous to those of a ball placed upon a smooth surface. If the surface is concaved upward, like the inside of the dish, the equilibrium is stable and the ball always returns to the low point when disturbed. If the surface is convex, like this one, upward, like a dome, the ball can theoretically be in equilibrium on top of the surface, but the equilibrium is unstable, and in reality the ball rolls away. Known as column buckles and collapses. If the surface is perfectly flat, the ball is in neutral equilibrium and remains wherever it is placed. As we will see in the next section, the behavior of an ideal elastic column is analogous to that of the buckling model that we just described. Furthermore, many other kinds of structures and mechanical systems fit this model. Okay, cool. So columns with pinned end. We begin our investigation of the stability behaviors of or are we done? I think that's all I got for tonight, because I honestly needed to roll through that before, but I think that was pretty decent. So we're going to end it with that. This equation is kicking my butt, but I think we did it. So hell yeah. So that's at least an hour. So thanks for joining me, and that's a video.